In this recording, we will discuss more about electrical circuits. Here we have a circuit that's made up of a light bulb, a battery, a switch, and wires. Let's go to the simulation that represents it. Here's the simulation. Now, what I'm going to do is ask the simulation to show me this in schematic form. This is the way it is shown in schematic form. Look at the battery, and actually we can do something more here and tell it to hide the electrons. Okay, now once we have that, so how is my circuit looking like? The battery, look at the way the battery is represented. Two bars, very much somewhat like a capacitor, except one of them is smaller than the other. The smaller one is the negative lead, the larger one is the positive lead. Remember, this is very much like a minus sign and a plus sign. You need to use more ink on the plus sign, so you need to use more ink on the positive lead. Now, wire is just a connection. A light bulb, schematically, is sometimes drawn like this, sometimes some other way, but that's not very important. A switch is just a wire. Now, if we open the switch, it's an open wire. Okay. Now, so this is the way it is. The battery, negative lead, the small one, positive lead, the larger one. The light bulb, this is more common schematic of a light bulb. Okay, this is a light bulb, and that's completing the circuit a wire. The direction of the current is usually flowing from the positive lead towards the negative lead. So this is the direction of the current. Usually we draw an arrow like here and designate it with I. We use I to represent current usually. Remember, current flows around the loop if the circuit is completed. Electrons flow opposite to the direction indicated by the current. Now, in the case of a light bulb, what's a light bulb made up of? It has two leads. These two leads take us inside the light bulb to what we call a filament. So that's what's inside the light bulb. Now the filament, when charges are going to flow through it, when the electrons are going to flow through it, they are going to make the filament get hot, and after they get hot, it's going to glow. And that's what's going to result in light. What does a battery in a circuit provide? It supplies current. However, be careful. Let's look at the circuit again. I'm going to show the electrons again, and let's remove the schematic view, have it lifelike. Now with the switch open, notice that we already have electrons throughout. All the conductors here are neutral, and they have equal number of electrons, of negative charges and positive charges. And what's represented here are the electrons in the outermost shell, the electrons that are free to wander around in the conductor. But they are already there. Now, what's going to happen when I close the circuit? These charges are going to be able to move. There is going to be a net force on these charges to move them in a particular direction. Now, the battery does not supply an excess of charges. See here, the same number of electrons go into the battery as go out of the battery. So the number of charges in the conductor or in the light bulb or anywhere in the circuit does not change. The battery is not going to supply charges to the circuit, but it's going to result into one type of flow. Okay, I'll have a circuit here. Let's build another quick circuit that's slightly different. Okay, I'll have the same type of battery, but I'll have a different wattage light bulb. So you see, I'm not going to put the switch and everything, so just to get it quickly. And look at here. See, the light here is not as much as the light here, even though we have identical batteries. Let's make it even more dramatic. You can barely see the light here. Okay, I'm not sure if you see it with the recording, but you can barely see it. But notice the motion of the charges. They are moving very slowly. Or in other words, the number of electrons that pass any particular point in the circuit at every second is less than what we have here. We have a larger current here than here, because the number of charges that move across any point in the circuit at any second is less here than in this circuit. So in other words, the batteries result in a current, but it's not a constant current. The current is going to depend on the circuit. They supply a current, but not charge. The charge in the circuit does not change. But what's important is batteries provide a constant voltage. D-cell batteries, for example, it's 1.5 volts. When you combine batteries, then you can get more voltage. You have 9-volt batteries that we purchase quite often. Now, going back to this, look at this circuit. It's not lit up. I can have another battery with a higher voltage. This one is a 9-volt battery. So let's go with a 50-volt battery and look what it results on. So now, because I have a higher voltage battery, suddenly I also have a larger current for the same light bulb. The battery is going to provide a constant voltage. We can measure that voltage with a voltmeter. Like here, it is given us 9 volts. That's what the battery provides. Now, even if I change my light bulb, the battery is still providing us 9 volts. Here, it's providing us let's see, 49 point. Okay, so I didn't mark it correctly here. I meant it to be 50 volts. Okay, there 50 volts. It provides us with 50 volts, no matter what the light bulb here is. That's the key of a battery. It supplies a constant voltage. One note though, ideally, for example, your car battery. Ideally, usually it provides about 14 volts. But once connected in the car, it's going to provide something like closer to 12 volts. And depending on the load, it's going to be more or less than 12 volts. So ideally, it's a constant voltage. In real life, okay, and the simulation here allows you to do it, we can right-click on the battery to change its properties. Then it has what we call internal resistance. If it has an internal resistance, like real batteries do, let me put something like 2.25 here. Now, look here at the voltage. It's not 50 volts anymore. It's 48.82 volts. Let's change the light bulb. It's 48.18 volts now. Change the light bulb. It's 42.68 volts now. So the voltage across it is going to change because there are losses within the battery, and these losses are going to depend on how much current is going to flow in the circuit. So ideally, a battery is going to provide a constant voltage, but it's not always the case. Okay, now what's a voltage? We talked about it when we talked about electrical potential. It's very much like potential energy, but it's not potential energy. It's electrical potential, just electrical potential without the energy. The higher the voltage, the more work can be done to move a charge. Okay, so what is a voltage? A voltage is what we called before electrical potential. Remember, electrical potential is not energy. We said it is somewhat the equivalent of g times height for gravity. Now, the higher the voltage, or the level of the voltage, is going to give us an idea about the electrical potential energy. It's not the potential energy, but it's going to give us an idea about the electrical potential energy. For example, it takes 1 joule to push 1 coulomb charge through 1 volt. So the electrical potential energy is Q times V, where V is the electrical potential, Q is the charge, and the electrical potential energy is U. So it takes 1 joule to push 1 coulomb through 1 volt. In terms of units then, a 1 volt is just 1 joule over 1 coulomb. Okay? So a voltage is a potential, but it's not energy. Energy would depend on the charge. How much charge do we have? The other component of the circuit was the light bulb. And sometimes we are going to have what's called a resistor or any other device in the circuit. Now, the role of the light bulb or any device in the circuit is to dissipate energy. It's going to dissipate it as power. Power, remember, is energy per unit time or work over time. In electricity, when dealing with electrical energy, power is given by the voltage times the current. So a light bulb or a resistor or whatever device we use is going to dissipate energy, and at every second the amount of energy dissipated is going to be V times I times 1 second. Now, what do we call resistance? Focus on the meaning of the word resistance. It's actually a measure of how difficult it is for charges to get through the circuit. The bigger the resistance, the more difficult for them to get through. We usually use the label R for resistance, and we use that to designate that particular property for any device we use in a circuit. For example, the resistance of a light bulb, the resistance of a diode under a particular voltage. So we can speak of resistance for any type of device. And that resistance is how difficult it is for charges to get through. Now, the voltage drop across any device is related to the resistance of the device through this equation. V is equal to IR. So the voltage drop across any device, whatever device, is related to the resistance of that device through this expression, V is equal to IR. We'll get back to that later. Now, the other part that we had in the circuit is a switch. What's the role of a switch? Nothing. Just a wire to complete the connection. Now, what about wires? What's the role of wires? Again, just complete the connection. Okay, but let's be even more precise about that. Let's look at the circuit here. Let me go to this top one. Look what the wire does. It ensures that I have the same electrical potential from this end of the battery to the device we get to. That's one key important thing. The wire keeps the same electrical potential throughout it. Now, that's one wire, so let's go to this other segment. See here, it's 0, and it's going to be 0 throughout that wire. This connection here does not make any difference. A wire connected to a wire, both of them are keeping the same electrical potential, and in this case it is 0. And a switch is acting just like a wire, keeping the same electrical potential. To try to explain what happens in a circuit, we have a small simulation here. Okay, this is the circuit here. What we have, you notice charges moving this way, and then we have a device here, and then charges moving back. And this is my battery. So the battery is essentially, in this particular example, it is a smile factory. And what we call voltage is the size of the smile. So all what the battery does, it takes the charges in the negative lead and gives them voltage, a smile. And now they come out here with a big smile, and whenever they are in a wire, the smile does not change, constant voltage. Now we get to a device where we have resistance. The resistance means it's going to be interaction with particles that make up that device. The particles can be the ions, can be imperfections in that particular device. Now, you notice here through these collisions with these green nasty particles, the charges are going to lose smile. The more interaction they have, the less smile they have. In real life, in a circuit, that's going to translate into losing energy, losing voltage, changing the energy into the energy for the device here. And the minute we are out of the device, look at what's happening to our charges. They have no more energy, so no more smile. Now, let's look at this when we don't have a battery. When we don't have a battery, our charges are going to be moving randomly in the circuit, but none of them has energy. So they're going to be randomly bouncing around their position. Actually, the electrons might be moving a little bit more than that, but by moving randomly, we don't have any net flow.